In this section, we're going to be looking at what we call antiderivatives and rules of integration. So antiderivative would suggest that we are doing the opposite of finding a derivative, and that's exactly what we are doing. So what we want to recall is that the derivative allowed us to find velocity if we had a position function. Now we're basically doing the opposite. Let's say that we have the velocity or the speed of an object, and we want to find the position at any given time. So we're going backwards from what we did before. So before we get started, I want to look at these three functions. We have g of x, h of x, and m of x. What I would like to do is go through and take the derivative of each one. And each one is just using the power rule. So we have 3 times 1/3, and that gives us 1. Reduce the power by 1. Here we get negative 4x. Here we just get 1. And the derivative of any constant, of course, is just 0. So we end up with x squared minus 4x plus 1. Alright, let's look at the derivative of h. Now you notice that the first three terms are exactly the same. So if I use the power rule, I get x squared minus 4x plus 1. But this one is a different function than g. It has a constant of negative 200. However, what is the derivative of a constant? Still 0. So you notice that these two are exactly the same derivatives. Okay, let's take the derivative of the last one. And the first three terms, once again, are exactly the same. So I get x squared minus 4x plus 1. This time the constant was 0. But the derivative of any constant, including 0, is still 0. So we get the same derivative. So what we are going to do in this section is that I'm going to give you the derivative. So I'm going to give you what we just found. I'm going to give you this part here. Okay, what I'm going to ask you to do then is to go back and give me the original function that matches up with that derivative. So I'm going to go back and say, what is the original function that matches up with that derivative? This is called finding the antiderivative. So it's doing the opposite. Of finding a derivative, we're finding the antiderivative, or we're going backwards to find the original function. Another word for that is called integration. Now, one thing we want to keep in mind is that if I give you g prime of x, how do you know that you are not supposed to give me the function m or the function h? Notice that all three of these functions have exactly the same derivative, so if I'm supposed to go back to the original, how do I know to put a 15 or a negative 200 or a 0? How do we know what the constant is? And the answer is we would not know what the constant is unless we had a little bit more information. So what we're actually going to get is an antiderivative that is basically, what we get is a family of antiderivatives. So we get a family of antiderivatives. Each one potentially could have a different constant. So what we could say is that the antiderivative of all of these functions would look like this. It would look like 1/3 x cubed minus 2x squared plus x plus some constant that we would not know. And the only way for us to figure that out would be to have a little bit more information about the original function. So we see that there are many possible antiderivatives, give or take a constant. Finding an antiderivative means going back to the original function that we had given its derivative. Alright, so we would say that a function f is an antiderivative of f on an interval I if f prime of x equals f of x for all x and I. So for example, going back to what we had, we would say that this is the antiderivative, or the original function could be the original function if the derivative was equal to x squared minus 4x plus 1. So if I was to be given this as the derivative, this could be an antiderivative. So it may not be the antiderivative, but it could be an antiderivative. Okay? Remember what we said, give or take, that we would not know exactly what the constant would be unless we had a little bit extra information. So this constant we call the constant of integration. So the indefinite integral, and that's a key word here, this is kind of giving us the basic idea there that we are not given specific information. So we have, and the indefinite integral gives us a family of functions because of the possible different constants. So this is kind of the key for this entire section right here. Thus, when we take the antiderivative of a function, we will be adding a constant term c, so we're just going to put the letter c. We're going to add that at the end of the antiderivative to say plus some constant. Alright, so we have a symbol that we use for integration, and it looks like kind of an elongated S. So if I was to make it like, kind of looks like that. It looks like a stretched out S. That's called the integration symbol. Okay, whatever function that we are going to integrate is called the integrand, and c is called the constant of integration. The d of x that we have here is going to remind us that we are integrating with respect to one specific variable, and that might be x or some other variable, but it tells us what that variable is that we're using for the original function. Okay, so let's look at some examples. Okay. So it says here the rules of integration, we're looking at just integrating a constant. So we want to keep in mind something before we go forward. If I gave you the function 2x, so let's say that f of x was 2x, and I ask you to find the derivative of that. Well, the derivative of 2x would just be 2. So we want to think about going backwards. Now I'm going to give you the derivative and ask you to go back to the original. So if you just had a constant, then you would just put an x behind it to get back to the original function. Okay, so here we're asked to integrate 2 with respect to x. Now this dx is important here because it tells us what variable that we're supposed to be using when we integrate. So the answer here would be 2x. Now we're going to put plus c. So the answer is actually 2x plus c. Okay, why is that? Well, when I give you 2 as a derivative, what if the original function was 2x plus 3? What would the derivative of that be? Well, the derivative of that would also be just 2. So we don't know what the constant would have been. Maybe it was a 5. The derivative of 2x plus 5 would also be 2. So when we go back to what the original function could have been, the constant is unclear because the derivative of that would have been 0, and then we wouldn't have known exactly what constant it could have been. It could have been negative 100. Because if I take the derivative of that, I still get just 2. Alright, so when we have a constant, we're finding the integration of a constant, the antiderivative of a constant. We just put an x behind it, or whatever variable is used for the integration, and then we add plus c. So here we're integrating pi. Pi is just a number, so it's a constant. So we would get pi times x plus the constant of integration. Alright, e is also just a number. We've said that e was approximately 2.71 or 2.72, approximately. So since e is a constant, when we integrate, or find the antiderivative of that, we'll have e times x plus the constant of integration. Now, for all three of these, how could I check my answer? Well, all I'd have to do is take the derivative of this, and if I get just 2, or pi, or e, then I know that I've done it correctly. So I can always check my answer by taking the derivative and seeing if I get back what we had as the integrand. Okay, now the power rule. So this is a big one. This is important. The power rule. Let's say that we have x to some power, and we want to find the antiderivative of that. So we want to go back to the original function. So let's say, for example, that before, like we did before, let's say that we had x squared equals x cubed, and I wanted you to find the derivative of that. So like the last section, okay, what would you have done? Well, the first thing that you would have done is taken the 3 and multiplied it times the front of the function. So that's the first step. The second step would have been then to reduce the power by 1. So you would have said, okay, well, minus 1 from the power, that's the second step, and then there would be your derivative. So what we're going to do to find the antiderivative is we're going to do exactly the opposite. The first thing that we're going to do is we're going to pay attention to the power. So we're going to do exactly the opposite steps in exactly the opposite order. So the first thing that we're going to do is we're going to add 1 to the power. So that would be our step 1. which will give us x cubed. And then we're going to divide by that new power. So we're going to divide by 3. Now when we do that, notice that we get x cubed, which takes us right back to the original function. So this is what our rule says. It says to add 1 to the power, and then we're going to divide by that new power. And we're going to remember that we're also going to add in our constant of integration. Alright, so let's say that we want to go back to the original function if we know that this original function has a derivative of x squared. Okay, so how do we get to that? Okay, so we're going to take what we're given, x squared, we're going to add 1 to the power, and then we're going to divide by that new power. So we're going to divide by 2 plus 1. So we get x cubed divided by 3. We're going to add in our constant of integration. Now you could also write this as 1/3 times x cubed plus c, and this would be our antiderivative. Now how can we check it? Well, let's check it by finding the derivative. 3 times 1/3 we know would be 1. And then reduce the power by 1, we get x squared, and that was the original derivative there. Okay, so remember what we're doing is I give you the derivative. Okay, this is the idea. So I tell you now the derivative, and then you tell me the original function that I would have you started out with in the previous sections to get this as my derivative. So I can always check by taking the derivative of my answer and seeing that I get back the integrand. Alright, so step 1, add 1 to the power. Step 2, divide by that new power. Alright, so we have x cubed now as the derivative of some function. We want to go back to the original function where we want to find the antiderivative. The first thing I want to do is add 1 to the power, and that would give me 4. Then I'm going to divide by that new power. Then I'm going to add the constant of integration. So you can either write it like that, or you can write it as 1/4 times x to the 4th plus c. So either way, perfectly fine, same thing. Okay, here's where you want to be careful. What if you have a negative exponent? So when we add 1 to that power, so I have x to the negative 4th. When we add 1 to that power, so plus 1, we're going to divide by the new power, so that would be negative 4 plus 1. So negative 4 plus 1, that would be x to the negative 3 power, and then now I'm dividing by negative 3. So this would be the same thing as negative 1/3 times x to the negative 3 power, and then we're going to add our constant of integration. Once again, you can check your work by taking the derivative of this and seeing that you get back the integrand. Alright, so here's an important technique that will help you out a lot with a lot of the problems, is being able to pull out the constant outside of the integration. So for example, if I want to find the antiderivative of 2x with respect to x, so I want to integrate 2x. What I can do is I can go ahead and just pull out that constant that's being multiplied in, and I can just focus on the part that has the x. Alright, so what's the antiderivative of x? That's just x to the power of 1, so we'll add 1 to the power, divide by the new power, and then whatever constant that we brought out that was multiplied outside, now we're going to bring it down and multiply it times the result. Now what's nice about this is that sometimes this cancels things out. So I think about this as 2 over 1. The 2's are going to cancel, I'm left with just x squared. The last thing I want to do is add in the constant of integration. Okay, how can I check this? Well, I can take the derivative of x squared plus some constant, and I should get back 2x. Here we're asked to integrate 5x to the 2/3 power with respect to x. So first thing I'm going to do is I'm going to notice that I have 5 times. So that's a constant multiple of the function. So I'm going to bring that 5 outside, and I'm just going to focus on x to the 2/3 power. So I'm going to focus on integrating that with respect to x. Alright, so remember, how do we add 1 or subtract 1? So how do we add 1 to this power? So we have 2/3. So remember, we're going to add 3 over 3, so we're going to add 1. And our new exponent becomes 5/3. And then we're going to divide by that new exponent of 5/3. Once again, don't forget that you need to bring down and multiply that constant times our result. I'm going to write this a little bit differently. Anytime that I'm dividing by a fraction, I want to flip that fraction and multiply. So what I really have then is 5 times 3/5 times x to the 5/3 power. So when I flip the bottom fraction and I multiply times the result, these 5's are going to cancel and I'm left with 3x to the 5/3 power, and I'm going to include also my constant of integration in my final answer. Okay, once again, check your work there. Take the derivative of this and see that you get back to that integrand that we started with. Now, just like as in previous sections when we were going to take a derivative, anytime we have a square root or we have exponents in the denominator, we want to simplify those and write those as positive exponents. So the first thing I'm going to do is I'm going to rewrite this as 3 over, I'm going to write this as t to the 1/2 power. Now it's in the denominator, and to use the power rule I want to bring it up to the top. So that would be 3 times t to the negative 1/2 power. And now it's really easy to see that 3 would be a constant multiple, or 3 is just being multiplied in. So I'm going to bring the 3 out of the integration symbol. Okay, so now I can focus on integrating just t to the negative 1/2 power. So I'm going to add 1 to the power. So keep in mind that's really like adding 2 over 2. So I get t to the 1/2 power, divide by the new power, which is 1/2, and then I don't want to forget to include that constant multiple that I brought out. So we're going to multiply that back in. Now I want to simplify this because I have a fraction divided by a fraction, so I'm going to take the 1/2 and I'm going to flip it and multiply it times the top. So that would be 3 times 2, you can think about that as 2 over 1 if you want, times t to the 1/2 power. And so my final answer becomes 6 t to the 1/2 power plus the constant term of integration. Alright, so if we have square roots or exponents in the denominator, we're going to bring those variables and those exponents to the top, and of course they change signs. So for the next example, the first thing I want to notice is that I do have a variable that is in the denominator, and it has a positive exponent, so when I bring it up to the top, it's going to become a negative exponent. It gets multiplied times whatever's at the top. And this is maybe a little bit more difficult to see, but keep in mind that the 3 does not have a negative exponent. It had an exponent of positive 1, so it does not move to the top with the x to the negative 7th. But this is a constant multiple, actually, of 1/3. I can write this as 1/3 times x to the negative 7th. So the constant multiple that I'm going to bring out, that I'm going to multiply out front of the integration, is going to be 1/3. A little bit harder to see, maybe, because we're not used to thinking about fractions like that. But factoring that out, rewriting it, and then factoring that out or pulling it outside of the integration symbol helps with the integration, makes it a lot simpler. Because now I'm going to add 1 to the power, so that gives me negative 6, divide by the new power, negative 6, and then of course I'm going to remember to bring down my constant multiple. That was outside of the integration. Okay, now I'm going to multiply across. I get x to the negative 6th all over negative 18, and I'm going to include my constant of integration. I want you to notice something for all of these problems. Notice that once I have integrated, the long s, that integration symbol, is not there anymore. So you want to keep that in mind. Once you integrate, we do not have that integration symbol anymore. Okay, so right here is where I integrated. I added the power divided by the new power. Notice that this elongated s is not in my answer. Okay, same thing here. Once you add 1 to the power, you should have no more integration symbol in your answer. So as soon as you start by adding 1 to the power, notice that for all of these, as soon as I add 1 to the power, the integration symbol goes away, because that means you're actually performing the integration as requested. Okay, sort of like this idea here. If I ask you to take the square root of 4, you would not write that as the square root of 2. Why? Because I don't want you to take the square root again, right? Once you take the square root of 4, the answer is 2. Once you've performed the square root, you do not need the square root symbol anymore. The answer would just be 2, and you would not try to take the square root again. In this example, here, if you left the integration symbol in, so let's say you got all this work done and you wrote your answer as x squared plus c, then what you're actually asking me to do then is to integrate this again for a second time. And we're not going to integrate again. So be careful. Once you add 1 to the power, your integration symbol goes away, and you're just left with the answer. Okay. Okay. The sum rule. The sum rule says that we can integrate more than one term at a time. So I can actually separate. So I have 2 separate terms here. What I can actually do, and we'll rewrite as we go, I can actually integrate each term separately if I wished. So I'm going to write this as x to the, okay, the 3 is the index of the radicals, and we know we can write that as an exponent of 2/3. So this is my power, this is the index, so it becomes 2/3. And then what I can actually do then is I can say minus, and then I can integrate the second term separately. So that would be 9, and let's go ahead and bring this x to the power of 2. Let's go ahead and bring that up to the top of the fraction. So I can integrate each one of them individually with respect to x. Now eventually we'll kind of get away from actually having to separate them, physically separate them. You can always do that physical separation. Eventually we'll just get to where we'll just integrate each term individually. Alright, so we'll have a little bit of a shortcut. Okay, let's focus on the first integration then, the first term. The antiderivative of that, I'm going to add 1 to the power, which means I'm going to be adding 3/3. And then I'm going to divide by the new power. Alright, we'll simplify that in just a minute. Now for the next one, what I would like to do is I have this constant multiple of 9 that's being multiplied times the variable. So I'm going to go ahead and I'm going to bring that 9 out to the front of the integration. Okay, notice that I have not added a power yet. Now I'm going to add 1 to my power. So that's going to give x to the -1 power. Divide by the new power. And then we'll bring down that constant multiple of that we brought outside of the integration. So what we actually end up with is a -9 divided by a -1, that's +9. And then we're left with x to the -1 power. Alright, so here's our 2 terms. Alright, so we added 1, divide by the new power, add 1, divide by the new power. Now we'll keep in mind that as soon as I added 1 to the power, I dropped the integration symbol. So let's rewrite this to look a little bit nicer. We know that when we divide by 5/3, that's the same thing as taking that fraction and flipping it and multiplying by the reciprocal. So that's actually 3/5 times x to the 5/3 power plus 9 times x to the -1 power plus the constant c. So we're going to make sure we don't forget that constant of integration. Alright, once again, how can you check to make sure it was correct? You could take the derivative of these 3 terms and you should get back a form of that integrand that you started with. Okay, so the key here is the sum rule says if you have more than one term in the integrand, you can integrate each term separately with respect to x.